Bismillahirrahmanirrahim. This is my lecture about the course of thermodynamics having the course code of PHY331. This is a 14 lecture, and in this lecture I will discuss work, the concept of work, quasi-static process, and PV diagram, the pressure volume diagram for the quasi-static process. The first part of this lecture is devoted to the understanding the concept of work. Then we will move towards the quasi-static process, and then we will discuss the work in changing the volume of a hydrostatic system, and finally we will develop the PV diagram for a hydrostatic systems. Work is actually the displacement of a body under the action of force, and the direction of displacement and the force should be same. So actually we can write numerically the work is equal to F dot dx, where F is the applied force and dx is the displacement of the body along x directions. So if we can write a 3-dimensional motion, so we can write F dot d, but anyhow this is a particular 1-dimensional motion of the object, so work is equal to F dot dx. So mainly the work is divided into two categories. So one is the external work and other is called as the internal work. In the external work, the system as a whole exerts a force on the surrounding, and as a result of this force, displacement takes place. Both work done on the system and by the system is included in this category, the external work. The example of external work is a gas that is confined in a cylinder at uniform pressure with movable piston. So the piston can either move up, and the work is done by the systems, and when some force is applied on the piston will move down, and this is work done on the systems. So in both cases the work done is called as the external work, because the system exerts force on the surrounding and the displacement of the piston takes place. So this work is actually considered in microscopic thermodynamics, and generally when the word work is it means external work. So how we can explain this work in case of electrochemical cells, or maybe in case of some circuit? So if we have some electrochemical cells and that is connected to external circuit, so as a result of this external circuit, current is flowing in the conductor, and if it is connected with something like a rotating or like a motor, so the armature of the motor will move, and this energy is converted into work. I mean the armature of the motor is moving, and that could be used for any purposes. So similarly, changing magnetization in a magnet that create eddy current is nearby conductor, that is also used to do some work. We have the other type of work that is called as the internal work. So internal work is the work done by one part of a system on other part of the system, and this work is called as internal work. So the example of internal work is the interaction of molecules, atoms, or electron on either other. Normally when we use the word work, it means external work. Internal work is just like presented here for the basic understanding. So we have two types of work. One is the work done by the system, another is the work done on the systems, and for that particular cases we can represent it by positive and negative signs. So when the resultant force acting on a mechanical system is in the direction of displacement of the system, then the work of force is positive. I mean we are applying some resultant force on a mechanical system, and it is in the direction of displacement of the systems, then the work of the force is positive. This is called as work done on the system, and this increases the energy of the system. And the other is work done by the system. When the work done by the system is regarded as a negative, this work is done at the cost of the system's energy, because the system's energy, this move the piston moves up, and this is work done. This is called as work done on this system. Work done on this is called as work done by these systems. So we have this second part of this lecture is about the quasi-static process. The quasi-static process actually, before understanding the quasi-static process, actually a continuous process in which the system is considered to be in equilibrium state. Normally we say that when the system is in mechanical equilibrium, chemical equilibrium, and thermal equilibrium, so it is in thermodynamic equilibrium. But when the properties of the system changes, then the equilibrium state is disturbed. So the quasi-static process is considered to be a process in which the systems continuously remain in the equilibrium, in the thermodynamic equilibrium. So normally a system in equilibrium should be in thermal, mechanical, and chemical equilibrium. When all these three conditions is satisfied, we can say that the system is in thermodynamic equilibrium. The mechanical equilibrium is simple. When there is no unbalanced force or torque acting on any part of the systems or the system as a whole, then we can say that the system is in mechanical equilibrium. Thermal equilibrium means when there is no temperature difference between parts of the system or the system and the surroundings, so then we can say that the system is in thermal equilibrium. And the third type of equilibrium is the chemical equilibrium, when no chemical reaction is taking place within the system, and as a result no motion of any chemical chemical constituent from one part of the system to the other part moves. So when everything is stable inside the system, so this is called as the chemical equilibrium. So a body or a system will remain in thermodynamic equilibrium if it is simultaneously in mechanical equilibrium, chemical equilibrium, and thermal equilibrium. So in case of a system in thermodynamic equilibrium with surrounding, there will be no work done by the system because it is in equilibrium configuration. There is no energy difference, and there will be no work done by this, there will be no work done by the system and on the systems. If an external force is applied, then the system will be no more in mechanical equilibrium. When some external force is applied, then the equilibrium configuration of the system will be disturbed. So there are different type of unbalanced force that are created, and that results the non-equilibrium configuration of the systems. The first is the unbalanced forces torque that may be created within the system due to turbulence or waves. So the system as a whole may execute some accelerated motion. So it means the mechanical equilibrium of the system will be disturbed and the system will be no more in thermodynamic equilibrium. The second unbalanced force may be created due to the turbulence or accelerated motion or a non-uniform distribution of temperature that could be created, and that as a result of this non-distribution a temperature difference is created between the system and surrounding. And what happen, finally a temperature difference is created that disturb the thermal equilibrium, and when the thermal equilibrium is disturbed, the system is no more in thermodynamic equilibrium. And the third case is that when chemical reaction may take place in the system, and as a result of this chemical reaction some motion of chemical constituent are created, and that creates some forces. So as a result the system's chemical configuration is changed and the system is no more in chemical equilibrium. So we can say that the system's thermodynamic equilibrium configuration has been changed. So the particular unbalanced power disturbs the equilibrium configuration of the system, leading to a non-equilibrium state. For an ideal situation, if we consider an ideal situation when the unbalanced forces are infinitesimally small, leading to an infinitesimally slow process, then this process having the system all the time infinitesimally near the equilibrium state is called as a quasi-static process. Actually, the quasi-static process an ideal process where the system is considered all the time in equilibrium configuration. Here, when some unbalanced force is applied on the system, then the equilibrium configuration of the system is disturbed. So what happen? We assume for the quasi-static process that if the change in the system is infinitesimally small, so the process will be infinitesimally slow process, and as a result we consider that the system may remain in equilibrium configuration. So such particular configuration is called as a quasi-static process. So why the concept of quasi-static process is important to us, and what is the purpose of introducing this concept? Actually, in different branches of physics, we have similar concepts like quasi-static process, that may be about the circuit in circuit theory or in mechanics, where we consider some ideal configuration. For introducing the concept of quasi-static process, it can make easy for us to do some calculation without addressing the complication of the system. Just like in mechanics, we consider some spring, and in that case we are not included the mass of this spring, so we consider actually it has some limited mass, but we ignore that. So normally that is a massless spring. Or similarly, we consider an ideal pulley because there is always friction between the pulley and that lever. So if we consider an ideal pulley in that case, so that is actually the example from the mechanics. So similarly, in circuit theory, we assume sometime that there is no resistance in a conductor or a battery having a constant voltage. That is not actually possible in reality, but we assume for simplifying or for simplicity of that particular system. So quasi-static processes are considered as similar to the reversible process because the dissipative forces are ignored. Say for example, if we ignore the frictional force, then the quasi-static hydrostatic process is considered to be a reversible process. So work done in changing the volume of a hydrostatic system. So how we can develop the work done, or develop the equation for the work done in changing the volume of a hydrostatic systems? We consider a very simple system. A gas is enclosed in a cylinder and there is a piston. The piston is movable, and we consider that the cross-sectional area of the cylinder is equal to A. Piston is equal to A. A pressure is exerted by the system at the piston face P. So what happens? This force on this piston will be is equal to the product of the area of that piston multiplied by the pressure. So this force will be equal to that is the internal force on the piston, that is equal to PA. There are some external forces from outside as well, so it depends upon the difference of two forces. If any force increases, so the body will move in the other directions. So here we consider the condition when external force is slightly different than the internal pressures. So what happen? The F is slightly greater than PA, so the piston will move in this direction. When the piston moves in this direction, so it will travel some distance, and the distance is represented by dx. So we can calculate the work done in this case. So this is the piston perform infinitesimal distance dx during compression, and that some positive work is done. So this is the initial state of the piston. When the force is due to the external condition is applied on it, the piston move from here to here. So infinitesimal distance is covered along this particular axis. So as a result of this compression, the system volume is decreased. So the work done due to this infinitesimal displacement is equal to dW is equal to F dot dx. So we can put the value of F over here, that is equal to PA dx. So the compression decreased the volume of the system, and that is why A dx is equal to minus dV. So what happened? We can put this value over here. So we can get the work done, infinitesimal work done in this case, that is equal to minus PdV. So the negative sign before the PdV describe the decrease in volume. So positive dV is the expansion process, the volume increases, and in that case negative work is done. But in this case there is positive work is done because the volume decreases. So for any particular finite quasi-static process, the volume when the volume changes from initial to final configuration, what happens? The work is done by the systems, and this work done is equal to minus integral in Vi to Vf PdV. So if we consider a quasi-static process, the change in volume and the pressure at all times is not only equal to the external pressure, but the pressure is a thermodynamic coordinate. So there will be a function of temperature and volume, which could be expressed by the equation of state. We can write the equation of state for this particular system. So the work done for this particular quasi-static process is equal to V work done is from initial to final configuration is equal to minus integral PdV into Vi to Vf. So moving the systems in opposite direction from F to I, what will be the work done if we move the piston in opposite direction? Just change the notation, but keep in mind in this case the work done is positive. So Wfi is equal to integral from Vf to Vi PdV. So this is actually for the quasi-static process. If we consider the work done in the one direction and the work done in the opposite directions, so that will be equal to the work done initial in moving the system from initial to final position will be equal to the negative of the work done in moving the system from the final to initial position. So this is a particular quasi-static process. If we remove the fractional forces and all other forces and make the changes infinitesimally small, then we can consider this process to be a type of reversible process. So we have some PV diagram, that is actually a pressure volume diagram for this particular hydrostatic systems. So when the piston moves, so volume changes are created inside the piston. So the position of piston at any particular moment is proportional to the volume of the system, and the pressure changes are recorded in the x-axis and the volume changes are recorded in y-axis. So this particular diagram is called as a PV diagram. So now we are going to develop a PV diagram for a hydrostatic system. We have different states in this PV diagram. In first case, we develop the system when it is moving from the initial state to final state. From this initial state to final state. Here in this case the volume of the system was decreasing because we have a positive work, and the volume of this system is decreasing. So the volume of the system is increasing. This is work done by the systems, and that is why this work done is negative. The volume of the system increases, but the pressure is reduced. You see, this is the initial pressure and this is the final pressure. This is the first part of the work, and the work done is given by the area under the curve. This is actually the shaded area gives us the work done. We have another case. This is actually the work done. The integral minus Vi to Vf PdV is the work done, and that is negative because this is work done by the system. We have another case when work done on the systems. This is the opposite of the first case. Initially the system moved from initial to from I to F. In this case the system, so keep in mind we can easily observe, we can easily see the system's notation from here. In this case the system move. This is actually this sign shows the direction of the motion of the system. You see the system moves from initial to final configuration, but in the second step what happened, the system moved from final to initial configuration. Here you see this is the arrow sign. This arrow sign shows that the system moved from F to I. So what is the work done in this case? The work done in this case is the area under the curve, and that is represented by the shaded area. So the volume in this case decreases the volume, but the pressure increases. So some positive work is done. So if we combine both the process, I mean the initial process where the system moved from I to F, and the second process where the system moved from F to I, so what will happen? We can find a loop, and the work done is present. I mean the work done can be shown by the area under the area inside the loop, that is the shaded area. So this is actually the combination of the first and second process. So the shaded area represents the net work done inside the system. So this is the PV diagram for a particular hydrostatic system, and then we can calculate the work done. So work done may be positive or negative in that particular case. So this is some discussion about the work, quasi-static process, work done in hydrostatic process, and the PV diagram for the hydrostatic process. Inshallah, in next classes we will move forward toward new lectures. Thank you very much.